In 2009, deep inside a blisteringly hot coal mine in northern Colombia, paleontologists were digging through layers of ancient rock formed just after the dinosaurs disappeared. They expected to find fossilized plants, fish, maybe the remains of crocodiles. What they did not expect was a single vertebra so massive it brought the work to a halt. The bone was thicker than a human wrist, far larger than anything that should have existed in a tropical rainforest 60 million years ago at first. The explanation seemed obvious. In Paleocene swamps, crocodilians were the dominant predators. Finding enormous bones in this kind of environment almost always meant one thing: a giant crocodile. But as researchers examined the vertebra more closely, something felt wrong. The shape was off. The curves did not match known crocodile anatomy. These bones didn't belong to any reptile the team recognized. Then the realization hit. These weren't crocodile vertebrae. They were snake vertebrae. And not just any snake. This was Titanoboa. As more fossils were recovered, dozens of vertebrae, ribs, and associated animal remains, the scale of the discovery became impossible to ignore. The bones were consistent, enormous, and unlike anything previously found. When scientists calculated the size of the animal, they assumed they had made a mistake. They ran the numbers again and again, but the results didn't change. Titanoboa was more than 15 meters long, over 50 feet from head to tail, and likely weighed well over a ton. For comparison, the largest anaconda ever reliably measured was about 28 feet long and weighed roughly 500 pounds. Titanoboa was nearly twice as long and several times heavier. It wasn't just the largest snake ever discovered. It was the largest land predator on Earth after the extinction of the dinosaurs. So how do scientists determine the size of an extinct animal from just a few bones? Modern snakes follow remarkably consistent biological scaling laws. The size of their vertebrae correlates closely with their total body length. By comparing Titanoboa's vertebrae to those of living boas and anacondas, paleontologists could extrapolate backward with surprising accuracy. And what those measurements revealed was an animal that pushed the limits of what biology should allow. But the real mystery wasn't just how big Titanoboa was. It was why a snake could ever grow that large in the first place. The answer lies in temperature. Snakes are ectotherms, meaning they cannot regulate their own body heat. Their metabolism, growth rate, and maximum size are all controlled by the temperature of their environment. In warmer climates, their metabolism runs faster. Digestion is more efficient, and growth can continue for longer periods of time. Titanoboa was not just a predator. It was a living record of an ancient climate. To understand Titanoboa, you have to step back nearly 60 million years into the Paleocene epoch. The planet was recovering from the mass extinction that wiped out the dinosaurs, and the tropics were unlike anything we see today. In what is now northern Colombia, average temperatures likely stayed above 32 degrees Celsius year-round, with little to no seasonal cooling. There were no cold nights, no winters, and no ice anywhere on Earth. The rainforest was a constant, sweltering steam bath, and that heat removed the biggest constraint on cold-blooded animals: energy. The fossil site where Titanoboa was found preserves this world in remarkable detail. Giant turtle shells the size of dining tables, early crocodile relatives with blunt, crushing teeth, and dense plant remains all point to a humid, swampy rainforest filled with slow-moving, murky water. This was not a fast-flowing river system. It was a tangled wetland where visibility was poor and sound was muffled by rain and vegetation. In an environment like this, size was an advantage. Titanoboa was not a fast-moving hunter. On land, an animal that massive would have struggled against gravity, dragging its weight through dense forest. But in water, everything changed. The swamps supported its body, allowing it to move with far less effort. Titanoboa likely hunted much like a crocodile, remaining nearly motionless beneath the surface, its body hidden among roots and fallen trees. It didn't chase prey, it waited. When something wandered too close, the strike would have been devastating. Biomechanical estimates suggest Titanoboa could exert hundreds of pounds per square inch of constriction pressure, easily enough to crush bones and stop blood flow almost instantly. Its diet likely included giant turtles, large fish, and early crocodiles, along with any mammals unlucky enough to approach the water's edge. Water was not just its hunting ground. It was essential to its survival, supporting its massive weight, aiding digestion, and helping regulate body temperature in an overheated world. So why did Titanoboa disappear? The answer is simple and unavoidable. The planet cooled. After the Paleocene, global temperatures dropped by just a few degrees over millions of years. For a cold-blooded giant, that small change was catastrophic. As temperatures fell, metabolism slowed. Digestion took longer. The movement became sluggish. A creature that required enormous amounts of energy to survive could no longer hunt efficiently or process food fast enough to sustain its body. At the same time, ecosystems were changing. The vast swampy rainforests began to dry out. River systems became more seasonal. Giant reptiles declined, and mammals warm-blooded and increasingly larger began to rise. The entire food web that supported Titanoboa collapsed. It didn't die in a sudden disaster. It faded away as the world it depended on slowly disappeared. Titanoboa didn't go extinct because it was weak or poorly adapted. It vanished because it was perfectly adapted to a planet that no longer existed. A shift of just a few degrees in global temperature was enough to erase the largest snake the world has ever known, and that is the real legacy of Titanoboa. Climate doesn't just shape ecosystems, it defines the absolute limits of what life can become.